Hello friends, I welcome you all to this session on power plant engineering. So today what I'll do is I'll try to model one uh, open feed water heater inside this particular cycle. So you can see that the problem says that a Rankine cycle operates between a boiler pressure of 5 megapascal. So this is the 5 megapascal pressure line and the condenser pressure of 10 kilopascal. So the condenser pressure is given to you as 10 kilopascal. And incorporates one feed water heater operating at 0.6 megapascal. So the pressure at which the steam is being extracted is 0.6 megapascal. Steam enters the turbine at 5 megapascal. Okay, this is the boiler pressure at which it is entering, and 500 degrees Celsius the temperature, and expand isentropically to the feed water heater pressure, where the fraction of steam is extracted for regeneration. Okay, the remaining steam expand isentropically, so the ideal work is there, and we will be also assuming ideal work for pump as well. The remaining steam the following feed water leaves the open feed water heater as saturated liquid at 0.6 megapascal. Now this is something which you have to understand. The feed water leaves the open feed water heater as saturated steam. So the exit state of feed water heater 6 is saturated. This is saturated liquid. This is very important. Now you have to find out the fraction of steam extracted. So let's say this is 1 kilogram. So I'm interested in finding out what is M, the net work output, and the cycle efficiency. So this is the cycle which we are going to model. So let us do what? Let us snip it and bring this onto our Excel. Okay, this was the question and this was my expected cycle. Now state 1 is basically what? First we have to write down the temperatures also. So the boiler pressure is 5 megapascal, so it is 5000 kilopascal. Okay, then the condenser pressure is only 10 kilopascal, so it is 10 kilopascal. The the feed water heater extraction is at 0.6, so this extraction pressure is going to be 0.6 into 1000, that is 600 kilopascal, and the turbine inlet temperature is given to as 500 degrees Celsius. So now at point 1 the pressure is going to be 5000, the temperature is going to be 500. Now what is required? Enthalpy. So it is enthalpy of steam based on pressure and temperature for water. So this is pressure, this is temperature, then comes entropy. So the entropy will be based on pressure and temperature for water. This is pressure, this is temperature. That's it. Point 1 is known. Now comes point number 2. So point number 2 is at what pressure? It is at extraction pressure. This is the one. What is the temperature? I don't know. What is the enthalpy? I don't know. But I know as this is isentropic expansion. So the entropy at point 2 should be same as point 1. Okay. Once this is known, then you can very easily evaluate the enthalpy based on pressure and entropy for water. So this is pressure, this is entropy. Likewise, you can also evaluate the temperature based on pressure and entropy for water. So this is pressure and this is entropy. So point number 2 is now known to you. Now if you want to see where is the state, so it should be outside the domain. So let us check it. So dryness fraction based on pressure and entropy for water. So this is the pressure and this is entropy. So this is coming out as 1. Why? Because this is not on the saturation state, it is beyond. And if you really want to see how much it is beyond, then you have to do what? You have to check the entropy of vapor corresponding to that particular pressure, that is 600. You can see that the saturated vapor entropy is 6.7 and the entropy which we are dealing with right now is 6.9. So it is way beyond this. So this point is in superheated state. So that's why this is coming out as 1, because in this particular state there is no point of dryness fraction. Dryness fraction only varies from 0 to 1. Now comes point number 3. So the pressure is the condenser pressure. the entropy has to be same as that of 1 and 2. So this will be the one. Then comes enthalpy, so we'll be doing the same thing, and then comes temperature, we'll be doing the same thing. So let us check whether we have done it correctly. So it is enthalpy based on pressure and entropy. Okay, so and this is temperature based on pressure and entropy. Okay, now comes point number 4. Point number 4 is again based on condenser pressure only, and the temperature will be nothing but the saturation temperature corresponding to water, corresponding to this condenser pressure for water. And now comes enthalpy, so it is saturated liquid enthalpy based on pressure. So that's it. Then comes entropy, so it is entropy based on saturated liquid for pressure. So that's it. So now we have everything. Now comes, so this. Okay, now comes point number 5. So what is point number 5? Point number 5 is basically the pressure which is the same as the extraction pressure. So this is 600. Now this is what? This is saturated liquid only. So we have to do what? T sat corresponding to pressure for water. This is the one. And then enthalpy. So we can do what? We can copy this formula here, and let us check whether we are on the right side. So this is okay. This is liquid based on this pressure, and this is entropy of the saturated liquid based on this pressure. Okay, done. Then comes 7. Now the point number 7 is at the boiler pressure. Okay, so what is this? 5. What we have done? 5. Okay. 5 point and 4 point should have same entropy. We have done it wrong. Sorry, friends. So this is wrong. So the entropy at the point number 5 should be evaluated from point number 6. That means this should have this entropy, and point number 4, sorry. So 5 entropy and 4 entropy should be same because this is isentropic compression. Once this is known, then you can tell that what is the temperature or enthalpy first. Let us evaluate. So enthalpy based on pressure and entropy for water. So this is pressure and this is entropy. Then comes the temperature. So this is temperature based on pressure and entropy for water. So this is pressure and this is entropy. That's it. Now comes point number 6. So point number 6 should have again the same pressure as the extraction pressure. So this is the one, and this is saturated liquid. So this is saturation temperature based on pressure. This is the one. Then the enthalpy of saturated liquid based on the pressure, this one. Then comes the entropy of saturated liquid based on the pressure, and this one. So now this is point number 6. Now point number 6 and point number 7, this is the pump. So the entropy at point number 7 should be same as 6. So this should be same as 6. The pressure at point number 7 is nothing but boiler pressure. So this is going to be the boiler pressure. Once this is done, then you can evaluate what is the enthalpy here. So enthalpy based on pressure and entropy for water. This is the pressure and this is the entropy. That's it. Now comes the temperature. So this is temperature based on pressure and entropy for water. This is pressure. This is entropy. Done. So point number 7 is also over. Now comes point number 8. Now what is point number 8? It is saturated liquid based on the boiler pressure. So this pressure is nothing but boiler pressure, and we are only interested in temperature as well as entropy, because these point 8 and 9 we only require for plotting, nothing else. So entropy for saturated liquid based on pressure. So this is the one. Now comes point number 9. So point number 9 is having the same pressure as that of boiler, and the temperature will again be the saturation temperature corresponding to boiler pressure. And then comes entropy. So right now, previously it was saturated liquid, but right now it will be saturated vapor. So this is the pressure, and that's it. So now you have every point. Now what is required? We have to find out so many things. So first let us evaluate the extraction. how much amount of mass has been extracted. So if you look this particular thing, then you can very well appreciate the fact that MH2, this one MH2 plus 1 minus MH5 should be same as H6. So H2 minus H5 will be H6 minus H5. Okay. Once this is done, then M can be evaluated as H6 minus H5 by H2 minus H5. So let us bring this also there for the time being. So this is the one. So first what I'll be evaluating is the mass flow, mass extracted. So this will be equal to H6 minus H5. So what is H6? It is H6 minus H5. This will be divided by H2 minus H5. So it is H2 minus H5, and that will come out as 0.179. Is basically the fraction, you say, or for 1 kilogram of steam entering, this 0.17955 kilogram will be the extracted steam. That's it. Once this has been done, then you have to tell what is the work output of turbine. So work output of turbine will be what? It will be 1 kilogram for this one. That is, let us also write this. So this will be 1 times H1 minus H2 plus 1 minus M times H2 minus H3. So this is the turbine work. What is the pump work? For this one, it is 1 minus M kg. So it is 1 minus M H5 minus H4 plus, for this one it is H7 minus H6. Then comes heat input Q1. So Q1 will be H1 minus H7. Okay, and what is the heat loss? It is, now this is, the mass is 1 minus M, so this will be 1 minus M H3 minus H4. So let us do what? Let us take this all there. So what is required? The turbine work. What is the turbine work? Turbine work is basically H1 minus H2. So H1 minus H2 plus 1 minus M. What is M? This is M times H2 minus H3. So that is H2 minus H3. So this is your turbine work. Then comes the pump work. So the pump work will be equal to 1 minus M times H5 minus H4. So it is H5 minus H4 till this point, and then plus H7 minus H6. So H7 minus H6, and that's it. Then comes heat input in the boiler, which is nothing but H1 minus H7. So it is H1 minus H7. Then heat exit, that is Q2, that will be 1 minus M times 1 minus M times H3 minus H4. So this is H3 minus H4, and that's it. Once this has been done, what you can do is you can evaluate the network output, and also you can do what? You can also evaluate the net heat output for verification. Then efficiency, eta. So eta based on network output, or you can also evaluate based on heat. Now, what is network output? It is the turbine work minus pump work. What is the net heat input? It is the heat added minus heat rejected. What is the efficiency based on work? It is nothing but net work output upon heat input. This is the one Q1, and then comes based on heat, it is nothing but 1 minus Q2 by Q1. So Q2 by Q1. So let us write them as efficiencies. So now you can see that due to regeneration, this is 40% efficient. And if there would have not been any regeneration, then uh, then there is no point, because this efficiency will reduce. So now friends, in this way you can solve your regenerative feed water heating cycle. And if you are interested in plotting it, we can also do it, no problem. So let us plot. So let us bring this TS diagram. So this is the one, and here we will be drawing the process one by one. So first what we will be doing is selecting data, and then one by one we will be adding the series. So first x-axis S1 S2, y-axis T1 T2. Okay, then add, then x-axis 2 3, and then y-axis T2 T3. Then add x-axis 3 4, and then y-axis T3 T4. Then add x-axis 4 5, and temperature it is 4 and 5. Then comes 4 5, then 5 and 6. So this is 5 6, and then temperature it is 5 6, and then okay, then add, then 6 7. So it is 6 7, and then temperature it is 6 7. And then comes 7 8. So this is 7 8. So 7 8, and then comes temperature. So it is 7 8, and then 8 9. So add, so it is 8 9, and then comes temperature 8 9, and then finally 9 1, and then x. So it is 9 1 x-axis, and then 9 1 y-axis. So what we have done so far is we have drawn everything, but we have not drawn this. So let us see how this looks. So this is our cycle. Now here there will be, so if I enlarge it little bit, this one, let us color it. Let's say it is black. You can see this is the one, and then there is a pump again, and then comes this process. Let us also make it black. So here you can see the slopes are different, and there is slightly something happening here. So this is basically your pump work. Okay, now we have to extract from this point, but how to do it? We have to draw this particular line. Now we have to, if this is 6, then we should have something called 6. This is what, this is 6 prime, let's say. So what we'll do is we'll add this 6 prime here, 6 prime, and what is this 6 prime? It is nothing but having extraction pressure as the pressure, and based on this we have to find out the saturation temperature corresponding to pressure, this one, and then the likewise, sorry, then the entropy of the saturated liquid corresponding to the pressure, that is this one. And once this has been done, then I can draw 6 prime first. So select data, add. So I have to draw x-axis. So what is 6? This is 6. What is 6 prime? This is 6 prime. And at the same time, temperature also 6 and 6 prime. Okay. Then 6 prime done. Then 6 prime to 2. So add x-axis. It is 6 prime to 2. Likewise for the temperature, it is 6 prime to 2. Okay. 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 So now you can see, now why it is not coming, because 6 prime temperature should be same as that of 6. Yeah, they are same. Then why this is a shift? So let us check it. Select data. Let us see the last one first. Edit. So what is the x-axis? Once more we do what? We have to first cancel it. We have to bring it down first. Okay, now select data, edit. So what is the x-axis? It is 6 prime. What is 6? This is saturated. No, sorry. We have done it wrong. Okay, let us correct it. This is saturated liquid. No, it should be saturated vapor. Now I think it has come. Okay, now you can see that you have been able to draw the cycle correctly. So friends, in this way you can model your Rankine cycle, which is not only having uh, boundary conditions like pressure and everything, but at the same time the cycle is also having one regeneration. That means a open feed water heater. So in the next lecture I'll tell you about the indirect contact feed water heaters and how to model them. Okay, or what we can do is we can also model this in your cycle pad. So this will be doing in some later videos. So in the next lecture I'll tell you that how to model a regenerative open and sorry closed feed water heater. Okay, thank you very much. Take care.